Hello friends, I welcome you in lecture number 5 on singularities and zeros. In this lecture we will see the relationship between poles and zeros of a complex function. We will see how to use the information from zeros of complex function to decide the poles of the same function. So for that we consider this result. This result says that suppose complex function f of z is analytic at some point, say z0, and suppose this point z0 is a 0 of nth order of this function, then 1 over f of z has a pole of nth order at the same point z0. So if z0 is a 0 of nth order of this function f of z, then z0 is a pole of nth order of the reciprocal of that function, which is 1 over f of z. So we understand with the help of example. For example, suppose we consider this function f of z equal to z times e raised to z minus 1. So we can see for z equal to 0, value of this function is 0, and if we find out first derivative, then we have to apply product rule. Z as it is, derivative of e raised to z minus 1 is e raised to z minus 0, that is e raised to z, and e raised to z minus 1 as it is, derivative of z is 1, and we can rewrite this by taking e raised to z common. So we have e raised to z into z plus 1 minus 1. Now if we calculate value of first derivative at z equal to 0, we have z equal to 0, so this becomes 0 plus e raised to 0, which is 1 minus 1. So first derivative at z equal to 0 is 0. Now we check second derivative. So again we apply product rule here. E raised to z as it is, derivative of z plus 1 is 1, and z plus 1 as it is, derivative of e raised to z is e raised to z, and then we calculate value of second derivative at z equal to 0. So it is e raised to 0, which is 1, plus 0 plus 1, which is 1 into e raised to 0, that is also 1. So second derivative is non-zero at z equal to 0, and value of function at z equal to 0 and first derivative at z equal to 0 are 0. So therefore this function has a 0 of second order at z equal to 0 by the definition of 0 of nth order, because second derivative is non-zero and first derivative and 0 derivative, that is value of function at z equal to 0, are 0. This function has a 0 of order 2 at z equal to 0. So if we take the reciprocal of this function, which is 1 over z times e raised to z minus 1, then this function has a pole of second order at z equal to 0. Because this function has a 0 of second order, its reciprocal function has a pole of second order at z equal to 0. So this is very useful result. If a function f of z is analytic at some point z equal to z0, then if z0 is a 0 of nth order of f of z, then z0 is a pole of nth order of reciprocal of f of z, which is 1 over f of z. We consider generalization of that result. Instead of 1 over f of z, now we consider a reciprocal of two functions, p of z over q of z. So suppose these two functions p and q are both analytic at a point z0, and suppose value of this function p at z0 is non-zero, and this function qz has a 0 of order n at z0, then this quotient has a pole of order n at z0. So this quotient has a pole of order n at z0 if p of z0 is not equal to 0 and z0 is a 0 of nth order of function q. So if z0 is a 0 of this function q of z, which is in the denominator, then z0 is a pole of this function p of z upon q of z, provided p of z0 is not equal to 0, and of course p and q must be analytic at a point z0. So again I repeat, suppose we want to decide the poles of this function. So suppose these two functions are analytic at some point z0, and suppose value of this function p at z0 is non-zero, and suppose z0 is a 0 of q of z of order n, then z0 is a pole of order n of the quotient function p of z upon q of z. So using this result we can determine the poles of some functions. So we consider first one, f of z is z plus 1 over z plus 3i. So we consider, suppose p of z is z plus 1 and q of z is z plus 3i. Now q of z is 0 at z equal to minus 3i. So first we find out value of q of z at this point minus 3i, which is minus 3i plus 3i equal to 0, and derivative of q of z is derivative of z, which is 1 plus derivative of 3i, which is 0. So first derivative is non-zero. This is non-zero for all z, and we are interested at particular value at minus 3i. So at minus 3i also it is non-zero because q dash z becomes constant. So therefore value of q dash at minus 3i is non-zero and value of q at minus 3i is 0. So therefore minus 3i is a 0 of first order or 0 of order 1 of function q of z. Also we have to check another conditions. So we have this pz and qz, both are polynomial functions, they are analytic everywhere. So that condition is also satisfied. P of z and q of z are analytic at every point, and therefore at z equal to minus 3i also. And of course we have to check whether value of function p at minus 3i is non-zero or not. So p of z is z plus 1. So p of minus 3i is minus 3i plus 1, which is different from 0. So now both the conditions are satisfied. These two functions are analytic at z equal to minus 3i. Value of function p at minus 3i is non-zero, and minus 3i is a 0 of first order of function q of z. Therefore by above result, p of z upon q of z has a pole of order 1 at z equal to minus 3i. Okay, so in this way we can decide. Now p of z upon q of z is nothing but f of z. So in the next step we will write f of z has a pole of order 1 at z equal to minus 3i. We consider second example, second problem. F of z is e raised to z over z minus 1 square. E raised to z over z minus 1 square. So here also it is reciprocal of two functions, which we denote by p of z equal to e raised to z, q of z equal to z minus 1 square, and both the functions are entire functions, so both are analytic at every point, and from this we can obtain that value of q of z at z equal to 1 is 0. And if we consider first derivative, it is 2 times z minus 1, so q dash at 1 is also 0. And the second derivative is derivative of this function 2 into 1 minus 0, so second derivative is non-zero. So therefore qz has a 0 of order 2 at z equal to 1, and value of function at z equal to 1, value of this function p of z at z equal to 1 is e raised to 1, that is e, so it is non-zero. And both the functions are analytic. P of z and q of z are analytic at z equal to 1, and value of function p at z equal to 1 is e raised to 1, which is e, and it is non-zero. So both the conditions of that result are satisfied. So therefore this quotient has a pole of order 2 at z equal to 1, because this qz has a 0 of order 2 at z equal to 1, and this is nothing but our function f of z. So f of z equal to this e raised to z over z minus 1 square has a second order pole at z equal to 1. So this is another way of deciding the poles of particular order of a given complex function. So in the next lecture we will discuss one another important definition of complex analysis known as residue of a complex function. I hope you like this lecture. Thank you very much.